to start talking.
Welcome. Welcome to AWS Database Tier Architecture Best Practices. My name is Siva Raghupati. I'm a solutions architect. I've been with Amazon for about 4 years. Prior to becoming a solutions architect, I was a technical program manager on the DynamoDB team. I wrote the first version of the DynamoDB specification. And later on, I was a development manager for Amazon RDS. And I'll be co-presenting with Matt Tavis.
Yeah, thanks, Siva. Well, we'll get back to Siva in just a minute. He's going to take a rest in the audience. We're going to sort of tag team this one. As Siva mentioned, my name's Matt Tavis. I've actually been with Amazon 7 years now. I actually joined AWS before these services existed and have had the honor to sort of be involved in the process and see them grow over time and work in the field actually with customers quite a bit as a solutions architect and now as actually a consultant for AWS. So I actually have enjoyed that time, and it's a great opportunity. And what I wanted to talk about today up front is kind of to give you a broader perspective of how we think about database architecture. It gets to be, a lot of folks associate database with specifically the relational database management system or service, and that is obviously one aspect of it, but when we think about data architectures in AWS, we have a much broader view than just a single database or an RDBMS. So I want to talk a little bit about that, give you a sense of the breadth of the platform there. And then after we've covered sort of a scenario to sort of show you how some of these things play out architecturally, I want to hand it back over to Siva, who will cover our best practices. So that's a little preview of what we're going to talk about today. But no story is complete without a little bit of history, a little bit of an analogy, right? So if you look at database architectures and sort of their history, you sort of get, it starts to feel, or at least when we looked at it and sort of did a little research, it felt much like a Swiss Army knife. It starts off very, very simply, right? It's a simple tool. There's a blade on it. You can do one thing, OLTP. It's transaction processing. It's got a table structure, transactions, locking, fairly structured model. And that's really sort of the origin of a lot of database technologies that people associate with our RDBMSs today, right? Over time, these things started to morph. People added workloads to it. Not just OLTP, but now we had OLAP, object-oriented databases. ORM models where people could write objects directly against a database model. And this actually added different types of workloads, different types of activity that people were performing against these databases. They weren't always transactions. Sometimes it was application processing, OLAP cubes. And it made that tool a little more complex. It got richer. Now we don't just have a knife. Now we've got a corkscrew, nail file. A couple other things get added to that. It starts to add to the richness of that tool. And then as you look at databases today in the 2000s, now it's doing analytics, it's doing clustering, it's doing a whole bunch of other workloads on top of that, in addition to just the simple OLTP that was its origins, right? So it's really evolved pretty drastically from a features and functionality perspective. And so now we have this, somewhat complex Swiss Army knife. It's actually now hard to fit in your pocket. But it's there. You have that feature for you. What this has generated with a lot of our customers is what we're calling a database anti-pattern, right? Where the answer is, oh, well, this tool I have, this database technology, does everything. So what I'm going to do is I'm going to shove everything inside of it, and it's just going to be where I dump everything I need to persist, right? It's a fairly common pattern we're seeing out in the field, and what it's generating is actually perhaps not necessarily the most optimal use of the technology or even the resources that sit underneath it. Things like AWS, EBS, EC2 instances, things like that. So this is, kind of our new anti-pattern. We're seeing a lot of customers sort of bringing that traditional software database model to the platform and saying, oh, well, this is, I'll just stuff it in the database and that's where it's going to be. What we're seeing is that the answer is really that it's not one size fits all in this space, right? There's a lot of different capabilities inside of a database, but that doesn't mean you use a database for everything. It's not necessarily tuned for all the different types of workloads. And if you did try to do, OLAP, OLTP, analytics, all that in one particular tool, in one particular database, what ends up happening is you can easily generate some inefficiencies in terms of resource consumption, right? You're designing for peak of peaks. What's the hardest workload at the hardest point in time, right? Is it a heavy analytics job at the end of the month that I'm stuffing all this work into, and so I have to scale for that one particular point? Or, can I actually break this out? And can I use different database technologies or data source technologies to optimize how I consume resources under the covers? So that makes it hard to efficiently manage resources. And obviously, as you've learned over the time here in your experience with AWS, we're all about optimizing resource consumption, making sure that the curve of what you've got running and available to you fits exactly what your business model demands at that instant in time. So when we look at it, we think it's much more important to distribute these workloads into the right tools and technologies throughout the platform. Additionally, obviously as you grow up, a database, vertical scaling is one model, but as you add, additional nodes, additional shards and things like that, administrative complexity can get high on something like that. So it's trying to stuff everything in one model and then administering that in a very broad way can add some challenges from an administration perspective. Obviously, we have things like RDS, which help take some of that away, but still there's some complexities there that you're buying into that aren't necessary for all scenarios. So thinking about how to minimize administrative complexity is also important in this model. Now don't get me wrong, RDBMSs absolutely have their place, and there's scenarios where they have to be used. There's scenarios where there's applications that have been coded against it, products and platforms that require an RDBMS and are built against it, and of course there's obviously data schemas and data models that require a multi-table, cross-table joins, triggers, things like that are fundamental and critical, but that doesn't apply to every particular data scenario. And of course, this isn't getting easier, is one thing we've also noticed. It's not necessarily simple to think about your data model and how it's going to be day one, and it's how it's going to stay that way forever. Because the data we're collecting, and you're collecting, is growing, obviously, pretty quickly, and it's not structured all the time, right? In fact, the growth of unstructured data, things like log files, social media content, access logs, things like that are actually growing at such an increasing rate and are becoming more and more part of your applications and platforms. Processing those things, storing those things, analyzing that data is becoming critical and part of your data storage solution. It's not necessarily appropriate to say the structured table model is the only answer for every scenario. So, and as you see here, obviously lots of devices, lots of metering points are adding to this workload over time. So it's just going to get more and more complex, and it's going to get more and more unstructured, and you're going to have to think about how do I use the right tools and right technologies for each of these different data sources to get the answers that I need in the most efficient and cost-effective way. Obviously we got a lot of questions. I'm not going to zip through all these. These are just some great examples of questions our customers ask us about this. But it's oftentimes there's price-performance comparison, answers or questions that people ask. How do I get the right number of IOPS? How do I scale this thing? How do I reduce my management overhead? How do I migrate data into this platform? A lot of these, there's not a quick answer. We could probably take one of these questions and go dive deep on it and spend the next 50 minutes on it. So we're not going to do that, sorry. If you had one up here you really liked and wanted the answer to, I apologize. We're not going to spend 50 minutes on that. But fundamentally, the point being there's a lot of questions that are coming out there, and what we're trying to do here is really to give you some simple ways to think about how do you make these choices and these trade-offs, right? Our sort of mantra, if you will, from a database architecture perspective is choosing the right tool for the right job. And when you think about what tools exist, I think we take perhaps a little more of an unconventional viewpoint around what constitutes a database or a data source for your application. Because there's a variety of things that require persistence, provide manageability and data management, and provide queryability, indexing, and searching, which are all kind of aspects that get worked into this whole model. Starting from the far left, Amazon Cloud Search. Search doesn't necessarily traditionally fit into that definition of a database, but what is it other than a heavily indexed data store that has a quick access, high-speed ability to find and retrieve materials, much like what people might do with a full text search inside of a database, right? But Cloud Search is much richer than something like that. But it's maybe the right answer for certain types of data in your application, right? RDS obviously fits that more traditional database model where it is a MySQL, Oracle, or SQL Server engine that you can then spin up. You can use, obviously, read replicas, high availability to get, and that fits where you need that relational database structure model, and that's that particular service around that. ElastiCache comes up a lot. It's not so much a persistent store, which obviously is different from many of the other services up here, but it is the answer for a lot of high-performance scenarios where people say, you have to use a traditional database, but I really need that super low latency, high-speed, simple queryability to pull information out and to serve hot content out of my database, to reduce the load on the database layer. And of course, DynamoDB is the alternate. We have RDBMS is SQL, and DynamoDB is the NoSQL world. So much more of a simple, either single key or composite key kind of a model with a blob hanging off it, much more unstructured and flexible, but heavily managed and highly scalable. So it fits a very different type of model. We can talk through how that model plays out. S3 and Glacier wouldn't fit a traditional database model because there's no indexing in terms of searchability and things like that, but it does have it's a great way to store those blobs. So for example, we've seen this before, and customers will spin up a relational database and then start stuffing all the documents in the relational database. And it's like not necessarily the most optimal use of the resources that are being deployed in that particular scenario. It makes a lot more sense to index the documents, store the index in like a cloud search or a Dynamo, and then point out to something like an S3 for access of that information. Glacier, of course, we'll talk about briefly. It's really where things go to hang out and be highly durable, but not highly accessible. So much more on the data archival side of things. Elastic MapReduce is another data services technology. It's much more around data processing in most cases, but it plays a pretty big role in a lot of these data architectures because fundamentally, once you generate a lot of data or collect a lot of unstructured data in many cases, you want to process it, to learn from it, to understand what it is. And that's where EMR comes into play to process unstructured and structured data together, generating outputs which you might store in, say, a DynamoDB or an RDS. But it's part of that database architecture because it's part of the whole data pipeline. We'll talk a little bit more about that in a second. And of course, EC2, you can run whatever you want on there. Certainly a common model. When we don't have a managed service around it, EC2 is where you install it yourself and go ahead and manage that platform on your own. And then finally, Amazon Redshift, which I'm still getting used to the name. I just heard it yesterday for the first time. So, but Redshift is our new data warehousing service. So this is, now it's the analytics side. It's not the real-time what's happening in the application serving a direct customer request, but more I want to analyze what's actually happened in my application, and I want to look at my user logs. I want to analyze what customers are doing, and I want an aggregated view across, what is potentially terabytes or even petabytes of log and activity information, and I need a data warehouse to solve that. That's where Redshift comes into play in that architecture. So all of these are part of it. And the reason why they're all part of it is because there's different types of models for access, right? There's much more structured, complex query models where you'd see something like an RDBMS or data warehouse or search, where there might be multiple types of fields you can query against. The data itself has to fit a particular fairly structured format in terms of storage, and so you have to define that or understand that up front. And then you have things that are much more simple queries, still somewhat structured, like the DynamoDB or even ElastiCache, where it's a simple key, more of a put and get kind of a model, right? But you're pulling things in and out of that particular service, generally optimized for high speed, quick access, but a less structured, if you will, particular approach. And then in the unstructured world, you have the custom query where I have a really unstructured thing and I want to ETL the whole thing together, analyze it, generate maybe something more structured. That's the Hadoop EMR world. And then S3, where I just want to store things. I need a key to get it back out. But there's no query model over the top of that. Where I find it is really the other structured services, and then I pull that item back in. So that's kind of how we see the space, if you will, from a data services perspective. And of course, on top of all that, those are our managed services. In addition to that, we have our primitive services, right? I'm not trying to call EC2 primitive, but I just mean in an architectural sense that it's perhaps less evolved. Oh, that doesn't sound good either. Oh well, Darwin's not here. So you have lots of different instance types to choose from, and of course you can host any major data store that you choose. Obviously, have a lot of customers who want to run Postgres or Redis or Mongo or Cassandra, and when they go and run those platforms, they run them on top of EC2 directly, and then they have a lot of choices all the way up to our high one 4XL, which has backed by 2 SSDs to give you essentially up to 120,000 IOPS on the local disk. So you have a lot of interesting choices there around how you can build and manage that. Now the thing to note is that how you choose your storage technologies, whether it be ephemeral, using the local disk like with the high one SSDs, then you have to have application level replication so that if that node dies, you haven't lost the data because there's no persistence in that local drive. Or you can use something like EBS, which you can then snapshot. You can move from box to box, virtual machine to virtual machine, give you more flexibility but it doesn't necessarily, it's then off box. And of course, there's two models on that, which I'm sure you're aware of, the standard, kind of equivalent to about 100 IOPS per volume, up to the new 2,000 plus kind of model for provisioned IOPS. So a lot of choices there. And in this case, what you're doing is you're saying, I want full control. It's fine with us. You can have all the control you want. But fundamentally, you then, with that primitive, you get lots of flexibility, but it also adds lots of management choice and lots of management overhead. So it's a trade-off, right? With primitives and flexibility comes more control, but also more work potentially on your end to manage and maintain that platform. So those are some of the sort of the overview of the services. The other thing I wanted to sort of point out here is really more about our life cycle. The way to think about data, and this is kind of a simple little model to talk about how data actually has a life cycle. It's not a one-time thing. It's not you create a model for your data and it just stays in that model forever, right? It might come in during an ingest phase, fairly unstructured. You might need a medium level of access, but then immediately you want to put it into something like a search or a metadata service, like a Dynamo or a cloud search. Now you need fast access to satisfy customer requests. You need a metadata, a set of that data. You don't need all of it, but just a subset of that data. And so it has a much faster movement rate. It has a much higher demand on speed. So immediately you've moved from maybe a highly durable, but maybe not as fast storage technology to a much faster, highly durable technology, which might come with more costs, right? So now you got to think about, okay, how long do I keep it in metadata? Does it stay there forever? And maybe it does, fine. Maybe it sort of, over time, it disappears and goes into archival, right? So there's a whole other process for how you manage your data through its life cycle. Additionally, you might have things like logging, usage logging. You might be capturing web logs, things like that. Well, those things feed into your recommendations engine, how you might suggest what customers are doing, how you might actually go into analytics and analyze what's happening on the platform. So those things have a life of their own. They start off as highly durable but more medium level of access, but then they might move into sort of a recommendation service, which, like our metadata and search service, is going to have to be high speed, quick response to customer requests. But again, it's a subset, it's an analysis subset of the data that you're generating. So when you think about the life of data, don't think about designing the model for now, but think about how it's going to move layer to layer over time through the platform, and what are the requirements at each layer, at each part, because that will define which services might be used. And of course, we have our backup and archival and analytics, which are kind of more as the data sort of travels through its life cycle through the platform. And this is kind of a more of a visualization, if you will, of kind of how the services fit together kind of across a couple axes. One is the structure axes. Redshift being highly structured, but also extremely high volumes, petabytes of structured data in a data warehouse kind of a model. To the far right, you get something like S3 or Glacier, where it's fully unstructured, but incredibly high volumes as well, right? When you start going down, you see, you get the structure, something like an RDS or an ElastiCache. It's semi-structured or very structured, depending on the model, but the data volumes per node tend to be a lot smaller in terms of what it fits. So thinking about what the volume of your data set is, and then how structured it needs to be, will help you sort of find maybe where in this continuum that particular data might need to live. Unfortunately, there's no one right answer for every scenario. Sorry, let me rephrase that. There's a right answer for each individual scenario. There's no generic answer for all scenarios. So that's where you have to sort of think through what are the access models, what's the specific technology, and how does it fit from a structure and data size perspective, because that'll map back to resource consumption and ultimately cost. So if we look at sort of a generic architecture of how it all hangs together, your application sits on top, and in the vast majority of cases, your customers aren't hitting your data stores directly. So your application's in handling those requests and then passing them on. You're going to use things like search for the search results, ElastiCache for caching front ends over various other data tiers, whether it be DynamoDB or RDS. MapReduce will be used for analytics, and of course, S3 and Glacier down here at the bottom for storage of objects or things that are maybe unstructured that maybe need further analysis or later looks. There's also an implied concept here called a data pipeline, which is based on that previous slide where you saw the life cycle of data. Data will move from service to service over the life of the application, right? It might start out as some information in one of the web servers that moves into S3, then gets analyzed, and then moves into Dynamo, right? So things will move, and so thinking about how you're going to sort of, if you will, automate or analyze the data as it moves between the services and come up with a model for when it moves, how often it moves, what the right approach is for that scenario is going to be key to sort of think about the data pipeline and the flow over time and how you manage that workflow. So let's walk through a pretty simple example. A video streaming application. I won't name any names, but obviously there's a lot of streaming applications out there. There's a lot of scenarios where this actually makes a lot of sense. So if we're worrying about the upload side of things, we're going to have a lovely little video that slides in. The application is going to have to do some analysis of this. It doesn't want to store the video in the relational database, but it needs to know enough about it to actually find it again, right? So immediately you're going to generate things like metadata, user information, who did it, what the rights and permissions are, perhaps, for that particular piece of data. That video makes a ton of sense to put in S3. It needs quick access. Maybe you can use CloudFront. We'll talk about that in a second. But it doesn't. It's an unstructured object. It needs to be stored there. You need to find it again, so we need something for that. But the video itself makes a ton of sense. It's just an S3 blob, right? Whereas the metadata needs to be discoverable. It needs to be high speed. You need to be able to get to that metadata quickly at the back end of a search, or when somebody looks for that video, you want the title, the description, the tags, who owns it. That's something you could use DynamoDB for, because it's going to be highly, it's going to be scaled very, very nicely, scales, consistently with the amount of storage you're using, and the metadata relative to the videos. It also has a high-speed access model, and it's pretty much a put and get, right? I just want to know about this one video. Tell me the title, the description, the info, right? Now, you still need search, and you don't really want to scan a table in DynamoDB every time you want to find a video. So instead, you take that same metadata, excuse me, or a subset thereof, and you can store it in something like Cloud Search. Now you have a much richer model over which you can find and discover videos, which will return a little bit of information like a pointer that you can use to look up in Dynamo to get the metadata out and then serve that video up. And then, of course, last but not least, the user relationships. Who owns the video, what the permissions are, is it shared, is it public, is it private? That a lot of times leads into a much richer data model, right? User relationships, user membership to groups, group relationships, default privacy settings. A lot of these things tend to be fairly complex data models that actually a lot of times necessitate or speak towards more of a relational database approach with cross-table joins, triggers, validation of information. So a user data model around who's doing what and what the relationships are, a lot of times will fit very cleanly into a relational database model from a table structure perspective. Now, if we then move on to discovery, we obviously have to search for things. So the user searches, and of course, you hit Cloud Search. That's where you go find things. Now, Cloud Search is just really going to return you a little bit of metadata about that service. The most important piece of that metadata being really the ID, the document ID. There's a little bit of metadata on top, but the document ID is pretty much here's the videos that meet your specifications, what you're looking for. Right? That document ID, now, if it's a hot topic, if it's a video that a lot of people are watching, why go all the way back to the data store? It's probably going to end up in my cache. So this is where I use ElastiCache. I quickly look it up and say, hey, does ElastiCache know about this? I want fast response to that. I don't want to waste time. I know Dynamo's fast, but if I can make ElastiCache faster, I'll do it. So it's a way to sort of front load that information for hot or popular topics. Now, as it turns out, you don't always get a hit in your cache. So then you have to then go, well, what do I do if I miss? What if I miss that cache hit? That's when you then go to the source itself, DynamoDB, to pull out the title, description, metadata tags, all that kind of fun stuff. Pull it back into more metadata, which goes to the user. And then, of course, you'll notice the video hasn't been returned yet. That's because the metadata is now referencing where that video location is, and instead of serving it out of my application directly, I'm going to serve that out of S3 through CloudFront, right? So that's how I'm now serving and accessing all that information. Now, they could hit S3 directly if it's a less popular video instead of edge caching it, or they could go through CloudFront. Depends on what the right model is for that item. Now, if we look at recommendations, this is a really popular topic. We see a lot of folks doing recommendations these days. It's actually become more of an expectation than an added value feature. People expect recommendations. They expect that what other people are doing kind of model a lot of times in apps. And so applications, this is an example of where you got local storage of user logs, information on the web server, which are going to be aggregated over time, sort of dumped into S3 as a regular log rotation type model. That data can then actually be analyzed in Elastic MapReduce, where the icon spins. Very exciting. That took me a while to figure out. After the spinning icon finishes, we get metadata. We get a whole bunch of pointers and reference information to say, hey, if a customer looks up video X, you should recommend videos Y, Z, and 1. that metadata should live someplace that's fast, easily accessible, DynamoDB, and potentially even ElastiCache up the layer. The same thing occurs when you go into analytics, right? You've got, again, your user logs. They flow down into S3. S3 does the analysis. Or sorry, S3 holds it. EMR does the analysis. We get some spinny icons again. Wait for it. There we go. Yes. And this generates tables. So it actually generates data warehouse information, like aggregations of user activity, which then dump right into Redshift. And now you have your dashboard, your data warehouse information. So that's my part of it. I'm sure you're all curious about what are some do's and don'ts, some what to do, what not to do with some of these services. And so I'll turn that over to Siva, who's got more detail there for you. There you go.
So I don't have any spinning icons, so I'm going to go into the boring stuff of when to use, when not to use, what are the best practices. Oftentimes we talk to a lot of customers. As I'm doing a call with the customer, going through the architecture, reviewing what to use, what goes in my head is really, I have all of these services, when to use them, when not to use them, and what are some of the top best practices. Obviously, we don't have an hour for each one of them. I'm going to touch on some of the top, do's and don'ts and best practices here. So let's take ElastiCache. So for people who don't know this, it's a managed in-memory caching service. It's Memcached compliant, which means all your existing code that uses Memcached can use ElastiCache service. The primary thing that comes to my mind when I'm thinking about cache is a millisecond or 500 microseconds, right? Let's say if your cache cluster is running on an AZ, which is an availability zone that's different from your application, right? You want to build your application so it can fail over between availability zones. So your cache cluster may be in one of the availability zones. So typically, AZ to AZ is about a millisecond latency. And if the app is talking to the cluster in the same AZ, you're getting something in the order of 500 milliseconds, microseconds, access times, right? It depends upon the instance type that you use. I mean, the higher the instance type, like M24XLs will give you like 100 milliseconds, microseconds, and then like smaller instance types that M1 smalls maybe give you around 500 milliseconds, right? This is with the test data set that we did the testing with. The data that you want to put in cache is really transient. In case the cache node dies, the data goes away. So you really don't want to be storing your persistent data in a cache. The classic use case is, if you're going to everybody's going to the front page of your site, you're showing the most popular videos or most frequently accessed stuff. Behind the scene, the application is doing the same type of query. Give me the public videos or the most popular videos over and over again. Rather than hitting your database to materialize that result, you may actually take the string, do an MD5 hash of that, and stick the results, the key and the value in an ElastiCache cluster, and then go after the ElastiCache cluster to get the data. Okay, so this takes away massive read, CPU utilization, on your relational database, or if you're using a NoSQL store, you don't have to pay for the provision, read capacity units, to surface these, things over and over again. And then the second thing is, in some cases, what happens is you have counters, right? A page counters, or if you're in a game scenario, number of kills or whatnot, right? These are transient data. In some cases, it's okay to lose a little bit of data, the last few counts that you have. If you have a transient counter, it's much easier to put that on in ElastiCache rather than actually going after putting that in a database, because every time you put this in a database, there is locking, blocking, et cetera, going on. Even if you're putting in a NoSQL store, what happens is you're actually nailing one single machine at the end of the day, and then depending upon your throughput, it may not handle that kind of a request rate, right? So you want to actually put that in cache and then actually have some kind of a service actually collecting these aggregates and pushing it back to the database, right? So those are some of the primary scenarios. Typically, people tend to get somewhere in the region of 5 to 10x faster reads and writes by going to cache. So again, when not to use this, please don't store your persistent data in cache and expect that to be alive. It may go away. And then also when you have infrequently used data sets, right? So there's no point in putting that in cache because you're going to probably put a TTL on that and it's going to go away. I mean, you pay the extra price of warming of the cache and that'll never be used. So if you have infrequently used data sets, it's probably better off going to a data store. So some of the best practices, the top best practice is actually use TTLs. I mean, the shorter TTLs are better. It's amazing how many cases we see people don't use TTLs and complain about the data being stale, right? It's because you're hitting a cache and then you're getting stale data. It's always a good practice to pass on the memcache, the objects that you retrieved in your application. If you have multiple classes, you can pass that object along rather than each class going and hitting your memcached cluster to get back your data. So those are some of the top best practices. And then in addition to the cache nodes actually using the memory for your objects, there's also a little bit of a connection overhead in cache nodes. Oftentimes we feel if there's a large number of connections, if you have very few cache nodes, then the memory comes out of the same pool of memory. Therefore, you'll see a lot of swap. So whenever you see a swap, chances are you have a large number of connections to a specific node. You may want to increase the connection memory that you give, as well as potentially try to increase the size of the node in your cache cluster. So those are some of the top practices. Obviously, we have CloudWatch metrics and alarms that you can set on, that may page you or actually call another system to do the adjustments automatically. So those are some of the top practices here. Moving on to cloud search. When I move on to cloud search, what really comes to my mind is the Amazon.com landing page. Whenever I go to Amazon.com and I try to buy a product, I try to type in I was looking for a clicker. I was not sure if they would give me a clicker here. So if you type in a clicker, it shows you, oh, these are the top hits. On the left side, it also shows you, oh, by the way, the price range between, let's say $10 or $20 or 30 to 40, this many products have been found. We call that faceting in the case of cloud search. So if you want faceting or ranking, it is much easier to stick your data into cloud search and have it do this for you. Simply you send the search strings and it gives you a result set back, in a fashion that includes the faceting and the ranking as well. Again, there's no search expertise required. As Matt was pointing out, if you have metadata pertaining to a video or a photo, you literally convert that into a JSON or an XML. You put an object ID or a metadata ID there, and actually, stick that entire payload into Elastic, Cloud Search, and then it automatically builds the index for you. When I think about Cloud Search, I'm thinking about an index, for the data that I have. I'm not thinking of this as being a persistent data store. Again, don't put your persistent data in Cloud Search. You need to have a database actually keeping the persistent data. Just think of that as an efficient index for doing full text searches. The other thing is, data must be fully denormalized if you're dealing with the relational data with the one-to-many relationships. So in order to convert that into an XML or JSON document, you'll have to basically, do a denormalization and then have an object ID, which would be the parent ID, and then, put the payload as multiple items in your JSON payload or XML payload. In terms of the top best practices, you should batch your documents. We allow batch sizes of 5 megabytes. So typically, it'll be best to send batched updates to the service. And then the other piece is, don't stick all your complete metadata for your object. For example, Amazon.com has thousands of attributes pertaining to a product, right? What they stick in their cache is a subset of them that are very relevant for people when you're searching there. Those are very relevant for the search. In order to get the complete data, you'd actually go back into your relational or NoSQL database to get back the result set. And then also, in many cases, people are actually computing. In the keynote, actually, the founder of Netflix mentioned how important it is in their landing page to show videos that are relevant for you. What they're also probably doing is, computing a relevance score for you, and then they are sticking that relevance score, into each one of those videos, right? So I think, so in other words, if you want to, so you should probably also send a relevance score pertaining to the data set as part of the data set that you send to Cloud Search. So actually, you could actually tell it to rank just not on text relevance, but also factor in your own computed relevance, I think it's a best practice to go ahead and compute that relevance and stick that as part of your indexable data in Cloud Search. Also stop words. Depending upon your domain, some words may be very common for your domain. There's no point in the indexer indexing that and the search trying to find text relevance based on that. So we have the concept of stop words, which essentially tell the indexer not to search those words and also not to care about those words when somebody are typing in, to ignore those words. Make sure you give us the right set of stop words. The other piece is also increasing your query times are proportional to the amount of computations that the Cloud Search does. I mean, it's an in-memory index. It does literally thousands of intersections per second very efficiently and very fast in milliseconds. But yet, sometimes when I'm searching, let's say if you have a movie database, I'm indexing all the details in the IMDb movie database. I'm searching Gone with the Wind. If the user tells me, hey, I'm searching the title Gone with the Wind, and if you give them an option to search in the title Gone with the Wind, the search is much easier to find for the Cloud Search to find this data than actually trolling through a whole bunch of other irrelevant description fields. So wherever it's possible, it is best for you to hint us to search in a relevant area. So those are some of the best practices there. And then switching on to RDS. RDS is a managed relational database service. We support 3 engines: MySQL, Oracle, and SQL Server. And then when to use RDS. Again, this is a 2-part question. When to use a relational database versus not a relational database, and when to use RDS versus building your own database, relational database on top of EC2 and EBS. So typically, when to use a relational database, when you have a large number of transactions, when you have complex queries, obviously, relational database, even though it's an awesome Swiss Army knife to solve that problem. So I love Swiss Army knives, so I always try to carry one before all these rules came on the airplanes not to carry tools. Nevertheless, I think going back from RDS, when to use RDS again, RDS is fantastic. It handles backups, it handles high availability, it handles patching. It takes away the entire muck from from the DBA world. The backups are very reliably stored in S3, which has 11.9's durability, et cetera. So I think if you want to offload all of this and focus on your application development and semantics and tuning your queries, et cetera, it's clearly an awesome platform to use. Now, there are some limits there. It supports a 1 terabyte database is the maximum that you can use there. And then, so if you have a 2 or 3 terabyte database that you need, obviously you cannot use RDS for that. In many cases, customers these days come back to us routinely and say, I want to build a system that supports, hundreds or thousands of requests per second, right? And then in some cases, what happens is a single node, right? Most of the MySQL, Oracle, and SQL Server we support here as part of RDS are a single node. They're not a scale-out solution. So you can increase the size of the node by just pushing a few buttons in the AWS console, just modify database instance, change it from M1 small to M2 4XLs, right? All of a sudden, rather than 1.3 gigabytes of memory, in a few minutes, you are actually scaling your instance to have a 60 gigabytes of memory or 67 gigabytes of memory to be precise. So even though we allow that, but the maximum amount of memory there is 67 gigabytes of memory in an M2 4XL. So if your workload is going beyond that of a single box, right, then obviously this is not a good fit, in which case most likely a NoSQL solution would fit in fairly well. And if you're doing a very simple access pattern, as I drill down, as I'm talking to more and more customers, I drill down to the scenarios, what constitutes the bigger portion of the load. It typically turns out that 1 or 2 tables get nailed with that kind of a request rate among the entire schema. In many cases, it makes a lot of sense to actually move those 2 or 3 tables and explore the possibility of moving that to like a NoSQL source such as Dynamo. So I highly recommend you not put those tables in a relational database, for example. So some best practices around that. Some time ago, we launched RDS provisioned IOPS, which under the cover uses EBS provisioned IOPS. If you're running a production database, there is, in most cases, EBS provisioned IOPS is the best fit. It gives precisely what you don't want to do with the database is play games with. For example, the problem with EBS standard IOPS is Typically, you tend to get about 100 IOPS per volume. You can burst in some cases to 400 IOPS, but you may not be able to get even 100 IOPS. Let's say if there is a lot of users. It's a multi-tenant system behind the covers, and then we don't actually hard allocate the amount of resources an EBS volume gets. So if you want to have a predictable performance and guaranteed performance for the most part, you should be using provisioned IOPS. There is no reason for a database workload in many cases not to use provisioned IOPS unless you're in a test phase or or you really don't care for it. So also we support this EBS optimized instances. EBS optimized instances such as M1 large, M1 extra large, M24 XLs are the best instance types to use. In which case, what happens there is we hard allocate. In the case of M1 large, we hard allocate 500 megabits per second dedicated bandwidth on the instance to talk to EBS, and it's 1,000 megabits per second in the case of M1 extra large and M24 XLs. And if it's a production system, you should be using multi-AZ for high availability, which does synchronous replication to instances running in multiple data centers, right? When you do a write to the database, the write comes back after it is persisted to two data centers. All this happens in about 2 milliseconds when you look at the disk statistics, right? So there's a little bit of a higher latency, but it's well worth the price. If the node goes down, we automatically fail the endpoint over to the new instance. So if you're thinking high availability, you should be thinking RDS multi-AZ. Read replicas, again, if you have a workload where you have predominantly large reads and a lower amount of writes, I think by all means you can fan out the reads by using read replicas. So moving on to DynamoDB. Obviously, I wrote the spec for this. I'm passionate about this product. What we had in mind when we were designing this product was massive scale, predictable performance, and a simple query pattern. If you're doing gets and puts, and if your payload is anywhere in the region of, let's say, less than 64 kilobytes, this is the store for it. Most of the 1 kilobyte payloads, the put and the get latencies are in the order of about 3 to 4 milliseconds. In the case of a put, within the 3 milliseconds, we've durably written to at least 2 data centers. The put comes back. By the time the put came back, your data is persisted in 2 data centers. It's extremely durable. And then you can also control per table the number of read and write IOPS that you need. You can dial up the read, dial down the writes, et cetera, right? So these are independent knobs, right? These are not related. So you can, most of the developers, create a table, provision, let's say 100 IOPS or 10 IOPS, and then when they go to production, they simply call an API, say, here's the table name, increase the read IOPS to 10,000, increase the write IOPS to 20,000. Let's say if their application becomes popular, they turn that up to 100,000 and 200,000, right? Simply an API call, wait for a few minutes. Your read and write workloads are still going on at the old level while this is happening, yet, magically with no change in the application code, you have your database scaling up for you, right? So where not to use this, if you have complex joins, complex transactions, it's not the best place to use this. I see I have 6 minutes. I'm going to zip through this as many as I can. So I think if you have a massive reads and writes, there's 2 types of tables you can create. One, a table with a hash key and a hash range key. Typically, it's best to keep with the table with a hash key if you have massive throughput that you need. If you're using time series data, it's best to use a table per day. Let's say if you're recording instruments, you have a weather recording instrument that sends time series data or a stock ticker that comes along, usually have a table per week. What you can do is as you move forward, you can dial down the writes on the older tables. You're not writing to them anymore. You're writing to the current table. And then you can dial down the reads as well. You can keep the current table hot with the number of IOPS, so therefore you reduce the cost as well doing that. So it has conditional updates, and then it also allows you to model one-to-one relationships. Just watch out for hotkeys and hot partitions. We have a section on this in the docs. Go ahead and look at that one. MapReduce, obviously, for MapReduce, when I'm thinking MapReduce, I'm thinking large batch jobs, large amounts of data in the gigabytes or terabytes or petabytes, and then parallel scans, right? If you're using a Hive is a language, it is SQL-like, which can run a query that can scan your massive data set and do computations. So anytime you're thinking batch analytics, this is something that you should absolutely consider. When not to use it, right? When you need answers in seconds or seconds, this is not the best place to use it. When you have thousands of concurrent users, you may want to materialize the data here and put it in a relational store, but this is not the place to send thousands of concurrent users, for example. Now, some best practices there. Elastic MapReduce is seamlessly integrated with S3. So you should use S3 for storing your intermediate data and high computations, intermediate computations. And also use pod instances to reduce your cost, especially in your transient clusters, where you spin up a cluster to do a specific computation and shut it down. In many cases, it's best to tune the instance size rather than mucking around with your code to get the job done. Redshift, we launched this product today. It can take anywhere from store hundreds of gigabytes to petabytes of data. And then there's two instance types there, an XL and an 8XL. And then XL can keep about 2 terabytes of compressed data on disk. And an 8XL instance can actually keep about 16 terabytes of data on disk. So the classic scenario here is if you have complex queries for summarizing historical data, right? That's the classic use case here. Obviously, the updates are batched updates. And it supports compression. So the price-wise, it's about 10 times cheaper. Compression-wise, it can do about, we get about 10 times compression on disk. So it's a massive place to put, park lots of data that you're doing some sort of summarizations. What not to do with this? If you're thinking tens of thousands of requests, this is not the place to do it. We typically tend to think of it, tens of requests, churning or doing a lot of computations rather than pointing hundreds of requests. If you have hundreds of requests that you want to send, you want to do the computation here and keep it in a cache, or keep it in another. For example, MicroStrategy builds caches on top of this, right? They may be able to serve a lot more than tens of requests there. So you're thinking really about some kind of a mid-tier that keeps the cache and the computations being done in Redshift. Obviously, in terms of the best practices, sort out the ingestion pipeline. It has connectors to DynamoDB, as well as connectors to S3. What that really means is you log on using your, a Squirrel SQL or one of the command line tools into the service, and then simply say copy, from S3 bucket with the file with this prefix into my table. Here is my user, AWS user credentials, right? The secret access key and the AWS key access key. And bingo, you have multiple streams of parallel loads happening from both S3 as well as DynamoDB. That's what we mean by sort out the ingestion pipeline. And then the second thing is provision the right cluster size. As I told you, there are 2 types of clusters there. And then I think you can use, one of them. I think I'm going to skip. Not really much else to tune. There's no point. There's no adding indexes. We take care of that for you. It's columnar index. It's automatically compressed on disk. There's really nothing much else to do there. Obviously, S3, the top thing that comes to mind here is high durability, the 11.9's durability. So typically, for example, Amazon.com uses Oracle, and then we put the Oracle backups using RMAN into S3. Classic use case right there. In the case of a database world, you want to stick. I think of this as a blob store, right? Put your metadata in a relational or NoSQL store. Put your blob data into S3. So typically when I think of the latencies there, I think of like hundreds of milliseconds, right? If you need anything less than a 10 millisecond, I would not stick that into S3. So I would stick that into DynamoDB, for example. Typically, these payloads are in the region of, let's say, less than 64 kilobytes. If it's more than 64 kilobytes, typically you can stand about 100 millisecond latency or more. Try putting that in S3. You may be surprised what you can get by. And also the cost factor, right? Today we announced it's about 9 cents per gigabyte per month, right? Dynamo is about $1 per gigabyte per month. That's something that you want to keep in mind when you're thinking about these data store choices. With that, I'm going to wrap up. I have 30 seconds. So I'm going to give the slides back. It has some S3 best practices. And Glacier, the top point there is, it's a place to archive your data. It's a penny per gigabyte, right? I'm thinking about my photo backups completely differently. What used to cost $10 a month is going to cost a cent per month for me, right? The price you pay here is really for accessing it. It's going to take you like 3.5 to 4 hours to get your data back, right? If you cannot wait for 3.5 hours to get your data back. Don't put that in Glacier, right? It is frozen. So with that, I'm going to skip the best practices and end my session there. So to summarize, use the right tool for the right job. Hot data should go in caches. In DynamoDB, RDS, et cetera, colder data should go to the right side. Thank you very much. And then, by the way, if you really want a giant Swiss Army knife, a month ago or so, you can buy this on Amazon.com. Thank you again.